My name is Bill Brumley. I'm an assistant professor at Tampere University of Technology. I've been there for almost 3 years now. I'm in the laboratory of pervasive computing there. Today my talk is on cryptography engineering and the challenges that we face in that field. So very briefly, so what is cryptography? So here's one definition. Cryptography is, I think when most people think about cryptography, it's the confidentiality that comes to mind. So it's the study of mathematical techniques related to aspects of information security, such as confidentiality and these other aspects. So I think initially the first concept that comes to mind when people talk about cryptography is confidentiality. And so what that means is you have some piece of information and only people who are authorized to read that piece of information should be able to read it. This is usually the first concept that people think of with respect to cryptography. But the other ones in that list are also equally important. I'm not going to talk too much about them today, but we can do all sorts of things with cryptography, not just do confidentiality. We can do things like digital signatures and authentication. So it's not all about encrypting and protecting data. I'm going to go through some of those examples today. If you're interested in a good read on cryptography, I'm an engineer. I like this book. It's the handbook of applied cryptography. So it's very dry, but it's a handbook, but it's very good. Engineers like handbooks, so it's good. It's a little bit dated, but it's a good book. So the first type of cryptography that I think also comes to people's mind when you mention confidentiality is symmetric key cryptography. And so here's a very simple example of what symmetric key cryptography is. So we have Bob, who is one party on the top. We have Alice, who's the second party on the bottom. It's always Alice and Bob in crypto. So, and they share a secret key. So it's some secret that just the two of them share, okay? And Bob wants to encrypt some message and send it to Alice. And his message is evidently, "Hello, Alice." It goes into this encrypt box along with the secret key. Out pops some random looking stuff. This goes over the wire to Alice. She plugs it into this decrypt box with the same secret key, and "Hello, Alice" pops out. So this is symmetric key crypto that's been going on for, I should probably know how long it's been going on for, but thousands of years. So it's a very, very old concept. The second type of crypto that's very important in modern communication systems is called public key cryptography. And from this slide to this slide, not a whole lot changed, but it's actually a shift in the paradigm, I would say. So we still have Bob wanting to send a message to Alice. The difference here is that Alice has split her key into two parts. One is a public key, which anyone has access to. So if I go back to the previous slide, this secret key, only Alice and Bob had that secret key, right? On the public key side, everyone has Alice's public key. It's public. You can shout it, you can publish it in a newspaper, you can put it on a website. Only Alice has the private key that corresponds to this public key. And the paradigm here is that if you have Alice's public key, anyone can encrypt a message to Alice under that public key, so that only Alice can decrypt the result. So Bob wants to encrypt a message to Alice. She retrieves Alice's public key from wherever. He has the same message, "Hello, Alice." It goes into the encrypt box. Random stuff comes out. So this random stuff, since Alice is the owner of the private key that can decrypt this data, she is the only one that can actually decrypt this data. And so she receives the data, goes into the decrypt box along with the private key, and the message "Hello, Alice" pops out. So those are generally the two types of paradigms that we have in crypto. So you have the symmetric key part where the key remains secret but shared, and you have public key crypto where it's split into two parts, a public part and also a private part. Okay, so the theoretical study of different primitives that we have in crypto is usually done under what's called the black box model. So in both the slides that I was talking about, especially on the symmetric side, we had this encryption function, and that's in this box E here. And so what happens when you look at the model, it looks like this. You have a message coming in, and you have a key coming in, and the ciphertext pops out. This was the random looking stuff, right? it goes across the wire, and you have the decryption on the right-hand side. So when we want to study the theoretical strength of different designs of what goes in this box E, this is exactly the model that we use. And with this model, we need some kind of threat model. So if you're going to attack this, or you're going to prove some kind of security about this scheme, you need some kind of model. You need some kind of threat model. And the model, one of the models that I'm going to talk about today is you can do something called a chosen plaintext attack. So the attacker essentially wants to recover the key. And in the chosen plaintext attack, what happens is the attacker chooses different messages, looks at the output of the encrypted message, and is somehow able to take all that data and figure out what the key is. So that's a chosen plaintext attack. There's different variants of that. There's one called the adaptively chosen plaintext attack, which allows you to examine the output and choose your next input based on what that previous output looked like. So it's not just one model that we have. It's not just the chosen plaintext attack. You can also do adaptively chosen plaintext attack. And if you look at any block cipher, any modern block cipher starting from the 70s, this is exactly the type of attacks that they're supposed to defend against, these chosen plaintext attacks and things like this. So since the 70s, this has been the model that we've been using to prove the security of different designs of crypto systems. Right. So now I'm going to talk about my specialty, which is called side channel analysis. So we had the black box model on the previous slide. So when I was saying that we were proving the security of certain designs, that proof takes place on paper. But crypto is a very applied field. Cryptography is a very applied field. It's all about application. And so eventually someone has to take that design that you wrote on paper and they have to do something with it. They have to make a piece of hardware that's going to do that computation, or they have to make a piece of software that's going to do that computation. And there, the question is, how well does the implementation of that system match the model that it was proved under? And it turns out that they don't seem to match up pretty well. And that's what side channel analysis does. So in traditional cryptanalysis, where the only tools you would have are things like chosen plaintext attacks, and side channel attacks actually target the implementation of the crypto system that you're looking at. The academic study of this started with Paul Kutcher's work around 1996. The real world side channels that we look at are power consumption, electromagnetic radiation, timing, faults, bugs, and acoustics. Those are some good examples. So I want to go back to the model really quickly before I explain this picture. So if we have some device that's doing this encryption, the fact is there's going to be more outputs than just the ciphertext, because it's a computer that's doing this calculation for us, and the computer does lots of things. It consumes power. If it's consuming power, it's emitting electromagnetic radiation. So there's more outputs than just this ciphertext. And the question is, can we use those outputs to help us do the cryptanalysis? And the answer is usually yes. So what I have here on the right-hand side is one of my students doing electromagnetic radiation measurements. So what we have here is a small embedded target device. So we're trying to extract some secret from this device. It's just encrypting something in a loop. And in his hand here, he has what's called an EM probe. It's basically a fancy, expensive antenna. And that fancy, expensive antenna is hooked up to a not so fancy, it's a radio, basically, and it's measuring the electromagnetic radiation of this device while it's executing. And it's sending it to this radio, and then the actual signals are going to this computer here, and they're shown on the screen here. He's doing some kind of frequency analysis of the EM emissions to that device while it's executing. So, right, so it turns out we actually end up getting a lot more outputs than just the ciphertext when we're doing crypto. So we end up with something, instead of a black box model, we end up with something that looks like a gray box model. So the stuff on top is basically the same as the black box model, but instead of just the ciphertext coming out, we get something else sometimes, depending on the implementation. The device is consuming power. Can you measure the power that it's consuming while it's doing that? It takes time to do the computation. You can measure the time that it takes for the device to execute. So there's all sorts of different information that we can measure while the device is executing. So this model tends to match reality more than the black box model, which most of the designs we have are proved under. Okay, so I already talked about a little bit of what side channel analysis is, so now I want to talk a little bit about what covert channels are. So a very informal definition of what a covert channel is it's a channel that is not designed or intended to transfer information at all. So you're communicating in some way that the system was not really designed for you to communicate in. And when you go from, I think a nice way to look at side channels is you have a device that's communicating with you in a way that it doesn't know that it's communicating. So if you kind of think about it the other way, what if you had that device and you wanted it to communicate with you over EM emissions and things like that? It would be called a covert channel. So you somehow design that device so that it emits certain types of electromagnetic radiation, and you measure that and you use that to communicate. So if you start as a covert channel like that, like two devices are communicating to each other over this channel, you can think of a side channel as a reduced covert channel. So it's like you start with this covert channel where we're trying to communicate very cleverly, and it turns into a side channel when one of the parties doesn't actually know that it's communicating at all. So it's passing this information without even knowing that it's actually sending it. And that's how I like to look at a side channel. So I go through one example of a very popular covert and side channel called the cache side channel. And to do that, I'm going to explain a little bit about how my microprocessor works. So we have a small diagram for a microprocessor here. When it goes to execute code, the first thing it does is fetch that code from memory, and that's what the instruction fetcher does. So it fetches some code from memory to execute. This step is not important at all. When that code actually executes, it's passed to something called the arithmetic logic unit. This would be something that says a very typical operation for a processor would be add two numbers together. This would be a very basic operation. That would be done by the arithmetic logic unit. You get two inputs, A and B, and it writes out the sum here and writes it back into the registers. So what's kind of abstracted, well, not really abstracted away, but not much information is shown in what happens in this memory interface here. So I'm going to focus really on this little box that is the memory interface, and a couple of things are happening there. We're fetching instructions through the memory interface, and we're also reading and writing values to the registers from the memory interface. So this is data, and this is code. So buried within the memory interface is something called a data cache. So we have this principle of locality, which means that if you're using data or you're executing data once, it's very likely that you're going to be using that data in the near future or executing that code again in the near future. So instead of pushing it way out to main memory here, which would be very high latency, it takes a lot of time for the processor to go out and fetch something from main memory. You might want to have, main memory is huge, it's many gigabytes. So you might want to have some smaller cache of recently used values that you would want to store closer to the chip so you can fetch it faster. And we can see there's usually multiple levels of cache. You have level 1, which is small and fast, level 2, which is bigger, a little bit slower. You have level 3, which is again bigger and a little bit slower, and then you have main memory after that. So there's this whole caching hierarchy that happens sort of transparently to software within the memory interface. Now I'm going to explain how to use that cache as a covert channel to pass data. And this is the way it works. We have two parties, Alice and Bob, and they want to pass information through the data cache by measuring only the time it takes for them to read and write to their own memory space. We have Alice here, and Alice reads from two different addresses, which are Alice low and Alice high. And the way memory is split up is that we're going to say for this very simple design, if the memory address lies in the low region of memory, it can only go in this low line. And if it lies in the high region of memory, it can only go in this high line. So when Alice, we're going to say this cache has two lines, the low line and the high line. And when Alice reads from this address, the low data goes here, And when Alice reads from this address, the high data goes here. So the address, so right now the cache is completely full with all of, with only Alice's data. So Alice wants to communicate with Bob using this channel. So the next thing that Bob does is he wants to send either a 0 or a 1 bit. And we're going to say in this example, he wants to send a 0 bit. So what Bob does is he reads from an address called B low. So this is in Bob's memory space, but it's in the low region of memory. So what happens is when Bob does this read, it gets put in this line of the cache. But there's only space for one entry there, so it kicks out Alice's entry, and all that's left is Bob's entry here. So that's the state of the cache after this read. And then it's Alice's turn to play the game. So what Alice does is try to read from her original two addresses, which were low and Alice high. When she reads from Alice low, her data isn't in the cache anymore. It got kicked out when Bob did his read. So this is going to be a very slow read when Alice does it. But when Alice reads from the high part, it's still in the cache. So this is going to be a very fast read because it was served from the cache, whereas this one was served from main memory. So this is going to be very low latency here. This is going to be very high latency for this read. There's going to be a difference there. And so Alice now knows that Bob read from the low side of memory and kicked out that value because the latency was higher there. And this is how Bob passes 1 bit of information to Alice by using only the latency of reads to his own data. So if he wanted to send a 1 instead, the data would go here, and then the latency would be higher on the second read. So that's how that would work. So that's how two parties who really wanted to communicate through the data cache with timings as a covert channel, that's how they would do it, but you would never do that. So now we want to turn the covert channel into a side channel. So the fact is that software is using the cache transparently. Your software doesn't know anything about the cache. So it's communicating via this channel, but it doesn't really know that it's communicating via this channel. And it can't really control that it's communicating via this channel because it happens transparently. So with data cache attacks that were started to become popular around 2004, 2005, what happens is you have a victim process over here that's doing some kind of crypto. At the same time, you have some spy process here that's just behaving very maliciously with respect to the cache. And so what happens here is that the crypto is kind of oblivious to this. It's just encrypting like it's supposed to. The only thing the spy is doing is just hammering the cache. So it's loading a bunch of its own stuff into the cache, and it's measuring the access times to its own data. And those are going to be fast or slow. And if the spy sees some access that is fast, he knows that his data was in the cache. If he sees some access that is slow, then he knows that his data was not in the cache. And he infers that if his data was not in the cache, then it must have been kicked out by the crypto process, and it tells you something about the data access patterns of the crypto process. I'm going to skip this slide. And I'm going to give an example of some data cache data, timing data in just a moment, but first I want to go over this one algorithm that's used very often in public key crypto. So the inputs to this algorithm are B, E, and N, which are integers, and it's supposed to compute B to the power of E modulo N. And why this algorithm works is not at all important for this talk. We're just going to look at the side channel properties of this algorithm. So it basically does two things. In each iteration of this loop, it always squares a number. So this happens in every iteration. If the bit of the key that you're trying to protect, which is E here, if it's a 1, then it also does a multiply. So we have a square that happens every time, and we have a multiply that happens conditionally if the bit is a 1 and not a 0. If we look at the side channel properties of this algorithm, let's say somehow magically that we're able to distinguish between when the algorithm is computing squarings in this step and when it's computing multiplies in this step. The reason that can happen is that if you're using a schoolbook method to multiply numbers, well, to square numbers, you can reuse some of the cross terms. So usually squaring is slightly more fast to compute than multiplication, so that's why we might be able to distinguish it. So if we're somehow able to measure that from the side channel, and we see that this algorithm performed in 4 iterations of the loop, it performed these 4 operations. In the first one, it performed only a square. And we want to work backwards from that and learn what the bit of E was. So if in 1 iteration of this, it only performed the square, what does it tell us about the value of the bit? Any ideas? So if it only performs this step and not this step, then what's the value of the bit? It's 0. That's right, because it never did this multiply. So it tells us that this is not true, and a bit is either a 0 or 1, so it has to be a 0. So the bit was a 0 here. It's going to be the same for this iteration because it's also a square. Here we did a square and a multiply. So we did this step, but we also hit this branch. So what's the value of the bit for this iteration? It's going to be 1, right? Yeah. And then we have a 0 here. So somehow, this is the idea of side channels. So somehow we're able to get this computation trace, and by working backwards from that trace, it tells us something about the internal state of that algorithm. The cache is actually a little bit more complicated. So the covert channel I was talking about divided memory in just 2 chunks. And the top is a practical attack that we did started back in 2005. Memory is actually divided into 32 different chunks. So you have 32 different signals. What this is showing is timings of reading data from those 32 different regions of memory. And then we have time on the x-axis here. So, and the intensity of each pixel, it's a heat map, so the intensity shows the latency of those reads. So what you would like to work back from these algorithms, these are cache timings taken in parallel to that modular exponentation execution. And what you would like to infer is try to find out what that square and multiply sequence is from these graphs, basically. So you're looking for stuff that looks like squares and multiplies. Here, it ends up being that there's basically 2 types of operations that are happening here. I've spent about 10 years staring at black and white dots like this. So I have a lot of experience here. So if it looks like random stuff to you, it used to look like random stuff to me. There's basically 2 types of things happening here. So you have a chunk that looks like this, and it's also here, it's here, it's here, it's here, and it's here, and it's here. So those, what is that? 1, 2, 3, 4. Those 7 chunks represent 7 multiplications, and it turns out that everything that's in between are the squares. So this is real data captured from 2005. On the bottom, this is about 10 years of research between those 2 figures, but actually looking at the same algorithm in a way. So there's a lot of research that happened, and what we try to do is try to reduce the noise in this signal so that we can more accurately extract the sequence of square and multiply operations. So that's kind of what we do. I'm going to skip the protocol part of this because I think we're almost out of time and go to the conclusion. So I would say the outlook for my field, there's 2 very interesting directions happening right now. The first is called leakage resilient cryptography. I mentioned side channels basically exist because of a failure to capture them in the model. We started with this black box model, and that's not really reality. Leakage resilient cryptography says, well, let's change the model. If we're leaking stuff, let's try to model it and include it in the model. That trend started in 2004. I'm very skeptic to that field of cryptography, and I can talk about that later. The second is post-quantum cryptography. So quantum computers, I guess we're still trying to build one. Nobody has one. Turns out that when we do get quantum computers, it affects cryptography in a lot of ways because it really speeds up brute force search. And a lot of cryptography security is based on brute force search. So we would like to have designs that are somehow resilient to these type of attacks. And so that's the second field. I think I'm going to close with a quote by Adi Shamir, which was at the RSA conference in 2013. He said that post-quantum cryptography is something that we need for the future. And what Adi said was, we shouldn't worry too much about post-quantum cryptography, but we should think about post-cryptography security. And what he means by that is that very talented people have worked in crypto to do have a lot of very interesting theoretical results. So we know how to do crypto. The problem is that we don't know how to we're not very good at taking crypto and applying it. So somehow when you take it from the theoretical results and you try to apply it, stuff goes wrong. And side channels is a good example of that stuff going wrong. We still can't get it right. I've been working in this field for 10 years. It's not getting any better. So before pushing out to the next field, which is post-quantum cryptography, I think we should try to figure out how to use the stuff that we have now before inventing new stuff. So that's the progress that I hope to see in my field. All right, that's it. Thank you very much.